In this video, we're going to explore the basic theory behind the convolutional neural network, one of the most widely used deep learning algorithms for image processing. The convolutional neural network, or CNN for short, is a deep learning algorithm specialized for image processing. Traditional multilayer perceptron models handle images by simply flattening the pixel data into a one-dimensional vector, which may cause a loss of spatial structure and positional information within the image. In contrast, CNN overcomes this limitation through the following characteristics. First, CNN learns by focusing on local regions of an image using filters. This allows them to effectively extract local features such as edges, dots, and lines. By applying these filters across the entire image, CNN is also able to preserve positional information. This makes CNN effective at handling various transformations such as rotation, translation, and distortion. Let's start by looking at the basic structure of a CNN. As you can see in the diagram below, the structure of a CNN can be divided into two main parts: feature extraction and classification. In the feature extraction stage, the goal is to pull out meaningful information from the image. The convolution layer uses filters, or kernels, to scan small local regions of the image and extract important features like edges, lines, and textures. Next comes the pooling layer, which reduces feature map size to lower computation and adds translation invariance, making the model robust to small shifts. Then, we move on to the classification stage. Here we use what's called a fully connected layer. It takes the features extracted in the previous steps and combines them to determine which class the image belongs to. Next, let's take a closer look at convolution. Convolution is the most essential operation in CNN. The term convolution technically means a mathematical operation that multiplies two functions after flipping and shifting one, then sums the results. Here's how it works. You start with a small matrix called a filter. You place this filter on top of the original image, and for the part where the filter overlaps with the image, you multiply each corresponding pixel value with the filter value. Then, you add up all those results. The final sum becomes the value of one pixel in a new image. As shown in the diagram here, when you multiply the red highlighted part of the image with the filter and add up the results, you get the number 4. When you move the filter over to the next red area and do the same, you get the number 3. The filter slides over the entire image and repeats this process. Through this operation, CNN can turn patterns found in certain parts of the image into numerical summaries. In short, convolution helps transform complex image data into meaningful features that the model can understand and use. Next, let's talk about stride, which is another key concept in CNN. Stride refers to how much the filter moves when it scans across the image. For example, if the stride is set to 1, the filter moves one step at a time, either to the right or downward, performing the convolution operation at each position. But if the stride is 2, the filter skips over one step and moves 2 spaces at a time. The larger the stride, the faster the filter moves across the image. This results in a smaller output image and also reduces the amount of computation needed. However, if the stride is too large, important details might be lost. So, choosing the right stride value is crucial. It's all about finding the right balance between preserving image detail and computational efficiency. In short, stride is an important hyperparameter that helps control that trade-off between resolution and processing speed. Now, let's see how stride affects the output size in a CNN. When a filter scans over an input image, the size of the output is determined by both the filter size and the stride. There's a simple formula you can use to calculate the output size. Let n be the size of the input image, and f be the size of the filter. Then the output size is calculated as n minus f divided by stride plus 1. Let's walk through a quick example. If your input image is size 7 and your filter size is 3, when the stride is 1, the output size is equal to 5. When the stride is 2, the size is 3. As you can see, the larger the stride, the smaller the output becomes. That means less computation, but also lower resolution in the resulting feature map. So, by understanding this formula, you can make informed decisions about how to adjust your filter size and stride to get the output dimensions you want. A feature map in CNN refers to the output data that's generated after applying a filter to the input image. For example, in a color image like an RGB photo, each pixel contains values for red, green, and blue channels. So, the input image has 3 channels, and we represent its dimensions as something like 6 by 6 by 3. 6 by 6 for the width and height, and 3 for the number of channels. If it were a grayscale image, the number of channels would be 1. Now let's say we apply a 3 by 3 filter. In CNNs, the depth of the filter has to match the number of channels in the input image. So for our RGB image, the filter needs to be 3 by 3 by 3. When we apply this filter to the image, it multiplies values in the overlapping region for each channel, adds them all up, and compresses that information into a single number. That number becomes 1 pixel in the output feature map. And just like we discussed earlier with stride, the size of the resulting feature map depends on the input size, filter size, and stride. In this case, applying a 3 by 3 filter to a 6 by 6 input with stride 1 results in a 4 by 4 feature map. In CNN, we typically use multiple filters at the same time. Each filter is trained to detect different features in the image, like edges, textures, or patterns. That way, the network can capture a wide range of useful information from the image. Here's the key point. Each filter produces 1 feature map. So, for example, if you use 2 filters, each one performs convolution independently and generates its own feature map, resulting in 2 feature maps total. If your input image was 6 by 6 and each feature map ends up being 4 by 4, then with 2 filters, the output shape would be 4 by 4 by 2. Now, if you use 10 filters, you'd get a 4 by 4 by 10 output. That's a 3D feature map with a depth of 10. In short, the number of filters equals the number of feature maps, which also becomes the number of channels in the output. Now let's take a look at pooling, which plays a very important role in CNN. Pooling is an operation used to reduce the size of the feature map, and it serves several key purposes. It reduces the amount of computation, making the model more efficient. It helps to highlight the most important features, and it provides the model with robustness to changes in position, such as shifts or distortions in the image. There are several types of pooling, with the most common being max pooling, average pooling, and min pooling. As shown in the diagram below, max pooling takes the largest value, min pooling takes the smallest value, and average pooling calculates the average value in each small region. Among these, Max pooling is the most widely used. In max pooling, for example, we often use a 2 by 2 region as a window. We look at the values in that small region and select only the highest one to represent the entire region. This approach is effective because it tends to capture prominent features in the image. Next, let's learn about padding. When we perform convolution, the pixels at the edges of an image are involved in fewer operations compared to the central pixels, simply because the filter can't fully overlap with them. As a result, important information at the edges may be lost, and the size of the output feature map becomes smaller than the input. To address this issue, we use padding. Padding involves adding extra values around the edges of the input image before applying the convolution. The most commonly used method is called zero padding, where we fill the borders of the image with zeros. This helps to maintain the original spatial dimensions of the image after the convolution operation. By using padding, we can preserve edge information and ensure that the output feature map has the same width and height as the original input. The next slide shows the overall flowchart of classifying MNIST using a CNN. It illustrates the techniques we've discussed so far, such as convolution and max pooling, and shows the dimensions of the resulting feature maps. In the next video, we will implement a CNN through coding.